All right, so we're going to do optimization word problems. Now, a lot of times in the real world, you're looking for like an optimal solution. Okay? So, for instance, there's a reason that Coke can is the shape it is when it comes out of the drink machine, and there's a reason it's the size it is when it comes out of the drink machine. All right? Now, what we're going to do first is we're going to do a word problem where they optimize a box. Like, for instance, if somebody were to give me, say, some fencing, all right, and my job, I've decided I've got this 3 fence, I'm going to build a fence for my dog. And maybe I've decided I want to do it as a rectangle. Well, if I have 100 feet of fence, I could build a rectangular fence that's like 40 this way and 40 this way and 10 this way and 10 this way. Or I could build a fence, maybe it's like, you know what, I'm going to build it and I'm going to make it 20 and 20 and 30 and 30. I mean, there are lots of ways to take that 100 feet of fence. But now, naturally, I think I would want my dog to have more area than less area to run around in. So what would be the area of this fence? 400 square feet or meters or whatever it was. What would be the area of this one? 600. So that dog's got a lot more room here. So what I'm looking for is I want the greatest area for him to run around here. So that's the kind of problems we're talking about. You're trying to optimize something. In other words, you're trying to maximize something or minimize something. Okay? So what we're going to do is we are going to work the example 1 on page 260. Okay? Now, listen to what it says. Then we'll write some steps down in just a minute. Okay. So optimization word problems. Now, I'm a visual learner, so my first step is always to draw a picture if possible. You don't have to do that. That's just kind of my suggestion. If you're not a visual learner, that might not be helpful. Okay, but that tends to be kind of what I do. Now, again, I'm going to write down my given and my find. That just helps me kind of organize. What do I know? What do I not know? Then my suggestion would be to write an equation for whatever you're maximizing or minimizing. Okay, so you're going to write an equation for whatever is being maximized or minimized. I'm going to put in parentheses. That's called your primary equation. Because sometimes you'll have more than one. Okay, so that's your primary equation. Now, here's going to be the catch. You can only have one independent variable in that primary equation. Right, you can only have one independent variable in that primary equation. So what if you've got more than one? So if you have more than one independent variable, you're going to have to write a secondary equation and make a substitution. So you'll see me, I'll label them so I don't get confused. So you can only have one independent variable in that primary equation. If you only have one, that's great. But a lot of times you'll have more than one. So if you've got more than one independent variable in that primary equation, you've got to write a second equation. They call it a secondary equation. And then make a substitution. Okay. Now, once that primary equation has one independent variable, you're going to take the derivative of the primary equation. Okay, so once that primary equation has one independent variable, then you're going to take the derivative. Now, where do maxes and minimums occur? Don't they occur at critical values? So how do I find critical values? Remind me. Where the derivative is either what? Zero or what? Undefined. So I'm going to put find the critical value. And I'm going to remind you that's when you set the derivative equal to zero or where the derivative is undefined. Okay. So you understand you're solving that equation. Okay. So you're solving those equations. Now, I'm going to put number 7 and kind of start. You're going to verify the answer for me. We'll talk about how to do that in just a minute. Okay. Now, in your book, that is not a problem at all. In other words, the answers you get are always right. But in the real world, but all you really know when you get a critical value, all you really know is that's a max or a what? Or a min. But in the real world, it would be a terrible day at the office if your boss told you to find a maximum and you handed her a minimum. You see what I'm saying? So in the real world, you want to verify that you know what you have is what you think you have before you like hand it off. So we're going to talk about how you do that. All right, so let's go work this example. All right, so look what it says. All right, so example 1 on page 260 says this. A manufacturer wants to design an open box. Now, what does an open box mean? It doesn't have a what? No top, okay? Having a square base and a surface area of 108 square inches, as shown in the figure. What dimensions will produce a box with a maximum volume? So maybe I work in marketing, or maybe I work in shipping or whatever, and for some reason, we need to use a specific amount of cardboard to build a box. But naturally, we want a maximum volume. We want the biggest box we can build out of this particular size piece of cardboard. All right? So let's go do it. You've got your steps. I'm erasing them, but you can kind of remind me what they are. So what's my first step? Draw a picture. Now, what kind of box is this one? It's just an open box, and they show it that it's kind of a rectangular prism. Now, Dr. Dan has 0 drawing skills. So there we go. Hard to believe my son's a graphic designer. All right. With massive skills. All right. So I've got some kind of box. Now, tell me what it says about the box. What shape is the bottom of the box? It's a square. So tell me everything you know about a square.
Equal sides.
All the sides are equal. What are all the angles? Right, 90-degree angles. Everybody with me? All right. Then it says this. It tells me that the surface area of the box is what? What's the surface area? Is it 108? Is that right?
Yes.
All right. Is it square? What? Inches, centimeters? What is it?
Inches.
Inches. All right. So the surface area is 108 square centimeters. Square inches. And it says, what dimensions will produce a box with maximum volume? What am I asked to find? Supposed to find the dimensions of the box. So it wants to know how long, wide, and tall the box is. Okay? Now, is it asking me to maximize something or minimize something? What's it asking me to do? All right, it's asking me to maximize what? The volume. So that's what I mean by draw a picture if you can. Write down what you know and what you're asked to find. All right? And I might even put square bottom. You know what I'm saying? Now, so I drew the picture if I could. I wrote down my given and my find. Now your third step said to write a formula for whatever you're maximizing. So what am I about to write a formula for? The volume of that box. Now, how do you find the volume of a box? Like if I want to find the volume of this Kleenex box, what am I going to do? Length times what? Width times what? Height. All right. So length times width times height. Now, then I noticed, oh my goodness, what kind of shape is the bottom of the box?
Square.
It's square. So like if this is X, what's that length going to be? X. And then is that going to be X? No, right? We don't know, correct? In other words, it didn't say it was a cube. It just said that the bottom was a what? Like on this one, the bottom's a square, but it's obviously not a cube. Okay? Now, you can put Y. I'm going to put H just because they use H in your book, and you can follow the book if you get lost on something. Okay? But Y is just as good. So do we understand my volume would be what? X times what? H. So my volume is X squared H. Do we agree? And I've got a problem. What's my problem?
You have 2 variables.
I have 2 variables. How many variables and independent variables could I say you could have? Just one. Now, whatever you're maximizing or minimizing, this is your primary equation. Okay? So you'll see me kind of label it so I don't get lost in a minute. Now, my problem is I can't have X's and H's. I got to have either X or I have H. I can't have both. So I'm going to have to go write some other equation, some kind of secondary equation to try to make a substitution. So I go back and look. All right, what's something that I know that I haven't used yet? I know something about the surface area. I know that the surface area is 108 square inches. Now, here's a box. Let's pretend it doesn't have a top. All right, because I'm not going to rip the top off. How would I find how much cardboard it takes to build this box? How do you find surface area on a polyhedron like this? Add up the areas, right? So what's the area going to be of the bottom? What shape is that bottom?
Square.
Square. So what's the area of the bottom going to be? X squared. Okay? So X squared is the bottom. All right, now, what about this side of the box? What's the bottom? X. How tall is it? So what's this area? XH. What am I going to do? I'm going to add it, aren't I? Now, because the bottom's a square, what's going to be the area of all of these sides? XH. Another what? XH. Another what? XH. How many of them do I have? 4 of them. Now, what if my box had a top? What would be the difference? I have 2 of these X squares, but I only have 1 because I don't have a top on it. Now, sometimes it doesn't matter, sometimes it does matter. Is this going to be easier to make this say X equals or H equals? H equals. Because I've got an X squared and a what? An X. All right, so 4XH would be 108 what? Minus X squared, do we agree? So how would I solve for H? What would I have to divide both sides by? 4X. So h is 108 minus x squared over 4x. Do we agree on that? We agree? So I'm going to come over here and I'm going to make a substitution. V equals, and I'm going to plug this in for h. All right, so there's my x squared, so that's all right. But when I hit this h, I'm going to put in what? 108 minus x squared over what? 4x. Now, let's see if we can clean that up any. Can I make it look a little bit better? Well, let's do it the long way. All right, do we understand I have 108 x squared minus what? X to the 4th, all over 4 what? X. What can I pull out of the top? I can pull out a what? An x squared, but what can I pull out of the top that will help me on the bottom? An x. So if I pull an x out of the top, that's 108x minus x what? Cubed all over kind of x times 4, isn't it? 4x. So what will happen to those x's? Won't they divide out? Are we okay? So my volume formula is 108x minus x cubed all over what? 4. And that's my primary equation. Everybody with me so far? So according to step number 5, once I've got my primary equation with one independent variable, which is x here, what do? I take the what? The derivative. Now, this is me. You might not do this. All right. Here's what I notice. First of all, I don't really care for quotient rule. And I noticed that 108 is divisible by what? 4. So I likely would do this, but you don't have to do this. What do you divide 100? When you divide 108 by 4, what do you get? You got a calculator or a brain? What's 108 divided by 4? 20 what? 27. So that would be 27x minus x cubed over 4. Do we agree so far? Now, I've already confessed to y'all, I'm just not a real big fan of the quotient rule. So personally, I'd probably write it like this. What's the same thing as dividing by 4? Multiplying by what? So Dan doesn't have to use quotient rule. Now, can you use the quotient rule? Yeah, I'm just not a big fan of it. Okay? So all I did was just play a little algebra first. Okay? So that 5th step says once I've got it in the form I want it in, I've got one independent variable, I'm going to take that formula. And what am I going to do? Take the what? The derivative. Okay, what's the derivative of 27x? 27. Minus what's this derivative going to give me? 3/4 x squared. See, that was super easy and sweet. I avoided that question. So that's what step number 5 is. Take the derivative. If you go do the quotient rule, you get the same thing. Now, what do I do next? I've got to worry about where that thing what? Is 0, and where that thing is what? Undefined. All right. When is 27 minus 3/4 x squared going to equal 0? Well, that's when 27 is going to equal what? 3/4 x squared, isn't it? When I added 3/4 x squared to both sides. All right, how can I get rid of this 3/4? Multiply by what? 4/3. So if I multiply this side by 4/3, I've got to multiply that side by 4/3. So do we understand that's gonna give me just x squared over here? What's 4/3 times 27? This is so disappointing.
36.
You never get an under answer in the world. Okay, now. So what is x?
6.
It's +6 or what? And I want to see both. That's got two math answers, +6 and -6. We take the square root of both sides. Now, one of those answers though doesn't make any sense in this context. Which one doesn't make any sense in this context? The negative one doesn't make any sense. Okay? So I know that x must be 6. Now, what was the units I put in here? Meters, inches, feet, what was it?
Inches.
So this has got to be what?
6 inches.
6 inches. Now, have I finished? No, because I need the dimensions of the box. So I know it's 6 inches by what? What's the other box? 6 inches by, how do I know how high it is? Go back to that substitution that you had. Didn't you say over there that h was what? 108 minus what? X squared over what was it? 4x. Do we agree? So I know x is what? 6. So 108 minus 6 squared over 4 times 6. All right, you got your calculator. Go figure out what that answer is. All right, so the height is 3. So it's 6 inches by 6 inches by what?
3 inches.
3 inches. Now, that's the correct answer. But we still got to verify it. Okay? Now, there's 2 ways of verifying it. And you can do it either way you want to. One way we've gone over and one way we're about to go over. Okay? Now, here's the one way we've already gone over. On the test on Monday, how are you getting maxes and mins? Where are you getting those from? From the which derivative? The first derivative from the split point table. So you can go back and make a split point table. And then show me, look, that 6 really is a what? A max. That's one option. All right, here's your second option. There's a little theorem that we didn't go over yet that we kind of skipped over. And I skipped over it because nobody pays any attention to it until they need it. All right, so look on page 235 in your book. There's something called a second derivative test. Now, I'm not saying that you have to do it this way. I'm saying it's an option. Look what it says. Let f be a function such that the first derivative at c equals 0 and the second derivative exists. If the second derivative of that number is positive, that number is a relative minimum. If the second derivative is less than 0 at that point, then that's where you have a relative maximum. Now, what is it talking about? Here's what it's saying. Where over there was our first derivative equal to 0? When x was what? 6. Right? Now, I'm just too lazy to make a split point table. So here's what it's saying. If you take the second derivative and plug in 6, you need to know whether this thing is positive or whether it's what? Negative. I don't care what it is. I just need to know if it's positive or if it's negative. That's quicker. Now, let me show you what I'm talking about. What was our first derivative for this? What did we get? We got what? 27 minus what? 3/4 x what? Squared. So what would the second derivative be? What's the derivative of 27? 0. What's the derivative of this going to be? Isn't that gonna be 6/4, which is what? 3/2 what? X. So what's the second derivative? It's a negative 3/2 what? X. So what would happen when you put a 6 in there? You'd have a negative 3/2 times what? 6. Now, don't write down what it is, just write down, is it positive or negative? It's what? Negative. Now, this is going to seem backwards until you stop and think about it. Look what the theorem says on page 235. If the second derivative is negative, what do you have right here? A relative what? Max. So this proves that x equals 6 is a max. Now, you write that down and let me make sure you understand why. Now, if you'd rather do a split point table on first derivative, can you? Yes. Now, that seems backwards to people until you stop and think about it. What do we use second derivative for? Concavity, right? When the second derivative is negative, which way is it concaving? Up or down? Down, right? If something's concaving down, would it have a max or a min? It'd have a max. When the second derivative is positive, which way is it concaving? Up. And if something's concaving up, it would have to have a what? A min. So when you stop and think about it, even though it sounds backwards initially, it's not. Because second derivative deals with concavity. Okay? So let's review the process real quick. You draw the picture if you can. All right? You write down kind of what you're given and what you're asked to find, just to get organized. And always write down whether you're what you're maximizing or minimizing. I'm minimizing cholesterol level. I'm maximizing volume. So whatever you're maximizing or minimizing, you've got to have a formula for that thing, like we did. Now, once you've got your formula, step back and look. If you've only got one independent variable, take thank you, Jesus, and go on. All right? If you've got more than one, you've got to write some other equation to make a switch. So there's always enough information for you to write a secondary equation if one is needed. Then you substitute, and you have to have one independent variable in that primary equation. Once you have one independent variable in that primary equation, then you set that derivative equal to 0, and then you set it equal to what? Undefined. Now, look over here. Wasn't this our derivative?
Yes.
Is that thing ever going to be undefined? No. But double check it. Every once in a while, one will get there, like with an absolute value or something. Okay? So once you find out where the derivative equals 0, then you solve that equation. Or where the derivative is undefined, you solve that equation. That's going to be your answer. I just need you to verify it for me. So if you plug that into the second derivative and it's positive, you're going to have a minimum. If you plug that into the second derivative and it's negative, you're going to have a what? A max. And if that bothers you, make a split point table on first derivative instead. Okay? So does everybody kind of understand what we're doing? Now, is this on your test Monday?
No.
No, this is on your final exam. So I'm going to put some homework problems on this. Now, what I'm going to do is this. I'm going to put some review problems up. If you want to work them, I don't care. I'm not going to, you won't see me until your test. Everybody with me? But I'll just grab some problems kind of like this. Grab a few problems back out of the chapter before this on like implicit and the related rates and those kind of things. So your homework assignment for Monday is to study for your test. But I'm going to go ahead and put Monday's homework assignment up, which are these problems. Okay? So don't even look at these until after your test. All right? So what we're going to do is, like I said before, you're going to take your test on Monday.